In the previous session, we have seen some concepts about linear regression. And we saw that we can write the formula y is equal to mx plus c in this way. Now, in this format, it means that y is the output variable, x is the input variable, that is feature and label. Epsilon is the random error. Random error is nothing but difference between predicted value and actual value. Or you can write it as yp also, where yp and y dash mean the same thing, okay? Just different ways of writing. So error is nothing but difference in prediction and actual value. Beta 1, that is slope of the line, is nothing but m and intercept c. So if I write y is equal to beta 0 plus beta x plus epsilon, it is nothing but y is equal to, this is your c intercept, m x. Okay. Y is the same thing, beta 0 is the intercept, and beta 1 is slope. This is the way we usually write in algebra, and this is the way we usually write in machine learning. Now there is another way. Instead of writing y is equal to beta 0 plus beta 1 x plus epsilon, generally we write it as h of x is equal to beta 0 plus beta 1 x, okay, where h of x is nothing but y, which is predicted, where h of x is called as hypothesis. H of x is hypothesis. So the line that we plot, or that equation, is called as hypothesis. That itself is known as hypothesis. Okay. Here also it has been shown that beta 1 is the slope and beta 0 is the intercept. Now suppose this is an angle theta made with this right angle triangle. This is the angle theta made by the line with this triangle. Then we also know that the slope is nothing but tan theta. So this we have studied in geometry, trigonometry. Anyways, as I mentioned earlier, the error, either you write as E or epsilon, or difference between y predicted and y actual, or you may write it as y dash and y, or you may also write it as y cap or y hat minus 1. Okay, it all means the same thing. Where yi is each of the y values, it is the observed value or the actual value, and y hat is the predicted value or the value of y obtained after fitting the model with the best fit line. The goal is to minimize the sum of the squared prediction errors. That means whatever error is occurring, take its square and try to minimize this value on taking summation. Now, what does this mean is, as you can see in this particular formula, we know that the predicted value of y cap, so predicted value of y, may be either greater than the actual value of y, or it may be lesser than the actual value of y. So if we do y cap minus y, sometimes this value may be negative, sometimes it may be positive. So in order to tackle this difference in the magnitude, that is the sign, negative or positive, to eliminate this problem that we may face in calculations, we are taking the square, because we know that square of plus 2 is 4, square of minus 2 is also 4, That means square of a positive or a negative same number is same. So that is why we are taking the square. And this is the value that we need to reduce, minimize. Summation of the square of the errors in the machine learning algorithm. Okay, now this is what we are saying is linear regression. Why is it called as linear? Because there is a relationship between x and y. It may be a direct relationship. That means increase in x will cause increase in y, or decrease in x will cause decrease in y. Or it may be a inverse relationship. That means increase in x causes a decrease in y, or a decrease in x causes an increase in y. These may be the two possibilities in linear regression. And we observe that the power over here or exponent is 1 for x as well as for y. That is a linear dependency. Now, certain names like x can be called as input or feature, or you can call it as independent variable, or you can call it as predictor, or you can call it as explanatory variable. Similarly, y is called as outcome variable, or you can call it as label, or you can call it as the dependent variable, or you can call it as the response. Okay. Hence, whatever training data set we have, we'll give it as an input to the machine learning algorithm. This machine learning algorithm will generate the mapping function between input and output by learning from the data set. And then when we give any new input, it will generate the predicted output. This is the prediction. Hence, we have seen that the base formula is nothing but y is equal to mx plus c. From this, we generate based on this or similar to this, we generate the hypothesis, which states that h of x is equal to theta 0 plus theta 1x. Or sometimes instead of h of x, we can also write h theta of x. They both mean the same thing, okay? No need to get confused between them. Now, we will first see what is simple linear regression. Simple linear regression means you will have one feature and one label. So in your training data set, for simple linear regression, you will have to consider only two columns. One is the output column and one is the input column. That is the feature and the label. And each of the examples that are given over here, say 1, 2, 2, 2, 2, 2. Suppose these are the examples, training examples, then consider that all these, the number of training examples is m. The number of training examples is m, and each pair is represented as xi, yi. That means this is x1, y1, this is x2, y2, this is x3, y3, and this is x4, y4. In short, xi, yi. So please remember these terminologies. Here, this m means slope of the line. But here, this m we are taking as total number of training examples. So here, the value of total number of training examples in the data set will be 1, 2, 3, 4. M is equal to 4 over here. Now, this theta 1 and theta 0 are called as parameters. Okay, it is called as, these two are called as parameters. So in simple linear regression, we have two parameters, theta 0 and theta 1, where theta 1 is the slope of the line and theta 0 is the y-intercept. Now suppose theta 1 is equal to 0. Then what will happen? H of x, that is your hypothesis, that is your prediction, will become equal to theta 0. And theta 0, we know y-intercept is always constant. So your prediction, that means the value of y, h of x means the predicted output, that is predicted y value will remain constant. In such a case, we can plot the graph that for every x, value of y is constant. So let this be x, this. Whatever is the intercept value, suppose this is our y-intercept value, theta 0, then a straight line will be drawn. For every x, y value will be constant. Okay. Case number 2. If theta 0 is 0, then what will happen? H of x will become equal to theta 1x. This means that your output y, h of x means y, is equal to some value of theta, that means some slope, into x. That means y is directly proportional to x. That means increase in x causes an increase in y, and decrease in x causes a decrease in y. That means in such a case, we get a graph this way, or we get a graph this way. Increase in x, increase in y, or sorry. Increase in x, increase in y, or decrease in x, decrease in y. This is the first quadrant, and this is the fourth quadrant. So first and fourth quadrant. Okay, this is just in terms of plotting that we are seeing. Now, case 3, if theta 0 is 1, y will become, or you can say h of x will become equal to theta 1x plus 1. Okay, or instead of 1, you can take 2, 3, anything. So any constant value, say k. In such a case, your graph, that is, k will always be the y-intercept. Suppose this is the value of k. Then your increase in x causing increase in y will start like this on the graph. Note that the learning algorithm, based on the input data set, the learning algorithm depends on the input data set. Okay, so this is what we have seen. Now let us see what is cost function. There is something called as cost function. Cost function is given by 1 upon 2m into summation of I running from 0 to m of y hat minus 1. And this can be represented as a function of something. Now, how we'll understand it is a function of what? We'll discuss. Now, what is y hat minus y I? For every value of y that is present in the data set, for every label output, whatever our prediction is there, it will be for y1, it will be y hat 1 or y2 hat and y3 hat. So the difference between these, we have to take summation of all these differences and put it over here. And why is our summation running from 0 to m? Any guesses? 0 to m because we know that in our training data set, there are m training examples. That is why 0 to m. And this factor, 1 upon 2m, this will be used, this is a constant factor because m number of training examples will be constant. So this is a constant factor. And why 1 upon 2m is because when we take the derivative of this particular expression, this square and this 2 will get cancelled. Okay, that we'll see. Now, what is y hat? We know that y hat is nothing but our hypothesis, which is nothing but theta 0 plus theta 1x. Right? So instead of y hat, we can write h of x. So y hat is nothing but h of x, and h of x is this. So we can write j of something is equal to 1 upon 2m summation I is equal to 0 to m theta 0 plus theta 1 x1 minus yi. Xi, this is xi, this is yi. So we see that these two parameters, theta 0 and theta 1, where theta 0 is y-intercept, theta 1 is slope of the line, they determine the value of this entire expression. So this whole thing is a function of theta 0 and theta 1. Right? Okay. Now, Suppose we want to find an ideal condition. That means we want a perfectly linear relationship. Perfectly linear relationship means what? We should have for x equal to 1, y should be equal to 1. If x is equal to 2, y should be equal to 2. If x is equal to minus 3, y should be equal to minus 3. Means what? Whatever is x, same is the value of y. So whatever x we get, same will be the value of y. Whatever x we get, same will be the value of y. So we'll get a straight line linear relationship. Okay. Now, when will this particular thing happen in our hypothesis? What does our hypothesis say? Our hypothesis says that h of x is equal to theta 0 plus theta 1 x. If theta 0 is 0 and theta 1 is equal to 1, what will happen? Our h of x will become equal to 0 plus 1x, that is x. That means our predicted y is equal to x. Means y is equal to x. Means perfect linear graph. Now, previously also I've discussed that our objective is to minimize that error. That means indirectly want to minimize the cost function, which is given by j of theta 0, theta 1 is equal to 1 upon 2m summation I is equal to 0 to m h of x minus 1. We want to minimize this. Now, in order to minimize this cost function indicates the difference in the actual and predicted value, that is the error. So if we want to minimize this, we have a particular algorithm called as gradient descent algorithm. Now in gradient descent algorithm, so first of all, today what we have seen is what is hypothesis. It is nothing but the equation of the best fit line. Then we have seen something called as cost function, which is nothing but indication of the error. And now we are going to see something called as gradient descent algorithm. Which is nothing but a way to reduce the error or the cost. Just a minute. Okay, so now please note that suppose we plot a graph between theta 1 and cost function, then how will it look? Now cost function is dependent on the parameters theta 0 and theta 1. So theta 0, theta 1 are what? Independent variables, and hence they will come on the x-axis. So let us for now ignore theta 0. Let us say there is no y-intercept. Then what will be our hypothesis? If we are ignoring the y-intercept, our hypothesis is theta 1x. Okay, so for now, our cost function is only a function of theta 1. So if I want to write this, it will become 1 upon 2m summation I is equal to 0 to m. Because our theta 0 is ignored. And here we are plotting the cost function as a function of theta 1. Now, if a theta 1 value so for every theta 1, we need to find out the cost function. Now, when you plot this graph, if you take examples, like take any value of theta 1, say 1, 2, 3, and so on, you will observe that since this is a square, means kind of quadratic, the graph that you will plot, it will come in this U shape. Since it is a quadratic function, there's a square, it is not linear anymore. The cost function is a quadratic kind of function because there's a square involved. Whereas our hypothesis is a linear function since power of x is 1. So when you plot, you will get some graph like this. So for this particular value of theta 1, cost function is this. For this particular value of theta 1, cost function will be this. Okay. Now, in this entire graph that we have plotted, we can see that this is our optimal value. Why? Because at this point, what is the cost function? It is minimum. At this point, the cost function is suppose 5. At this point, the cost function is suppose 1. So if we draw lines like this, we are seeing that this is our minimum value of cost function. So for this particular graph, there is only one such minimum point. So this particular point, we can call it as global minimum. It is the global minimum point. Now, in a graph like this, if this is our graph, here, there is no global minimum. Why? Because this is one minimum point and this is one minimum point. So, in this much region, this is the optimum cost function. So it is called local optimum. In this particular region, this is our local optimum. And for the graph as a whole, then this is our global optimum. Okay. Now this is what a 2D graph, because we only have x-axis and y-axis. Suppose we make it 3D, then what will we have to do? We need z-axis. So what will come? What other parameter can we consider? We know that initially we have ignored theta 0. So now let us introduce theta 0. So now our cost function will become a function of both theta 1 and theta 0. And hence, what will happen is, let us plot theta 0 here and theta 1 here. And along the z-axis, we'll have our cost function j. Now in 3D, if you want to visualize, the graph will look, it is called as contours. The graph will have contours. For example, something like this. It will be 3D. Okay. So if I talk about the graph now, which is plotted with theta 0, theta 1, and j of theta 0, theta 1, we can see that this was our initial graph where we had theta 1 and j. This is how our graph will look in case of 3D. We can have theta 0, theta 1, and j. So as you can see, this is how the 3D, that curve will look. This is the curve in 1D. And this is the curve in 3D. So here, this particular point is the global minimum. Now remember, in linear regression, we do not have local minimum. There is only one global minimum. If you consider local minimum, then this is one graph that you can take as an example, in which from this particular point, this may be one minimum point, or this may be one minimum point, or here, and so on. So consider it to be a hill-like structure. Multiple hills are there. And to come down the hill from here, you may either come here, or maybe there's another steeper hill over here, you may come here. So consider the contours to be hills, and the actual graph that happens in case of linear regression is this one. Now, how does gradient descent help to reach this minimum point? What is the function of gradient descent? To reduce the cost function, means to find the minimum cost or the minimum error, means to come to this global minimum point. So wherever you are, for whichever values of theta 0 and theta 1, for whichever values, from that particular point where you are currently, how can you reach the global optimum? Means how can you alter the values of theta 0 and theta 1 so that you reach the global minimum point? That is done by the gradient descent algorithm. So gradient descent helps to choose theta 0 and theta 1 in such a way that your cost function is reduced. Your cost, your error is reduced. Means accuracy of linear regression, accuracy of prediction has improved. Now, gradient descent algorithm, we will see that actual algorithm, the steps that are done in that algorithm in our next lecture. Okay, thank you for giving me a patient listening. So in this lecture, we have seen some topics like what is hypothesis, what is cost function, and now we'll see how gradient descent will help us reduce the error. Thank you for this.